So your book gives you the example of sulfur. So in order to find the number of neutrons in an atom of sulfur, I would need to know what the mass number is. The most common form, or you could say the most common isotope of sulfur, has a mass number of 32, and we know that sulfur's atomic number, just by looking at the periodic table, is 16. So how would I find the number of neutrons in this common isotope of sulfur? I take 32 minus 16, and that, I believe, gives me 16, right? Yeah. So just one more time, to find the number of neutrons in the common isotope of sulfur, I take the mass number of that isotope, which is 32. 32 is the number, or the sum of the protons and neutrons in that atom, and I subtract from that the number of protons. So one way to tell the different isotopes apart is through this method, which involves writing the name of the element followed by its mass number. So the mass number, again, is the number of protons and neutrons in the nucleus. So an isotope of rubidium with only one neutron would have a mass number of 38, because 37 protons plus 1 neutron is equal to 38, so that isotope would be rubidium-38. Now the isotope of a rubidium atom with 2 neutrons would be rubidium-39, because 37 plus 2 would be 39, and so on and so forth. So an isotope can also be indicated by its isotopic notation. So here we just have basically the name of the isotope, but there's another way to identify them, and that's by this notation here. If you can't see it, I'm going to write it out bigger. So you have the element symbol. So in the case of sulfur, it would be S. On the top left corner, which this is where it gets a little confusing, because on the periodic table in the top left corner you have the atomic number, so it just gets switched. In the top left corner you have the mass number, which again is the sum of the protons and neutrons in the nucleus, and on the bottom left corner you have the atomic number, which is the number of protons in the nucleus, which we said in order to have a neutral atom of that element, the number of electrons is equal to the number of protons. But the number of electrons isn't relevant right now, we just care about the number of protons. Okay, so this would be the isotopic notation of sulfur. So we actually already know what each of these numbers is. So just to write it out correctly, it would look like that. So for each kind of element and its isotopes, you have the element symbol, the mass number up here in the top left, and the atomic number in the bottom left. And so it's very important to know which one of these is which, because if I ask you what is the number of protons, neutrons, and electrons in sulfur here, I would need to know what these numbers mean to be able to decipher that. So if I want to find out from this right here, the number of protons, neutrons, and electrons, the number of protons is indicated by the atomic number. I know the atomic number is located in the bottom left, so I know that there are 16 protons in the sulfur isotope. And I also know that in order to have a neutral atom of this, the number of electrons has to equal the number of protons. So there are 16. Now, in order to find the number of neutrons, I have to go back to this equation here. I subtract the atomic number from the mass number. So that's exactly what we did here already. We know that the mass number is 32. The mass number is located in the top left, and I subtract the atomic number from that, and I get 16. Now let's talk about the atomic mass. Finding the atomic mass isn't actually as simple as you think it would be. You cannot just add up the mass of the protons, neutrons, and electrons to find the total mass. Actually, the real mass of the atom would be less than the addition of those things because of something called its nuclear binding energy. There's actually several reasons why finding the atomic mass is tricky, that being one of them. Another reason is that elements in their natural state don't exist as just one single isotope. So your book gives you the example of chlorine. Chlorine naturally occurs as a combination of chlorine 35 and chlorine 37. So those are two different isotopes of chlorine. And those two different isotopes have different masses. So how is it that you can find an element's atomic mass if you have this combination of different masses? So what scientists basically had to do is come up with a new unit of measurement. So instead of using kilograms, which would also result with super small numbers that are going to be hard to work with, they use the atomic mass unit. So they basically had to come up with a new standard. So we know a standard is the thing that we compare something to find its measurement. So if I want to find the length of a table, I would use my standard of a ruler to find out how many or how long in meters that table is. So the new standard, the thing that the mass of the atoms is compared to, is the mass equal to 1/12 of the mass of a carbon atom with 6 protons and 6 neutrons. So the isotope of carbon, which is called carbon-12, is what the mass of other things are going to be compared to. So again, one atomic mass unit is equal to 1/12 the mass of a carbon atom with 6 protons and 6 neutrons, which is carbon-12. So basically what you have to do in order to find the atomic mass of something is you take its average, taking into account the percentage of the occurrence of each isotope. So let's say here we have an atom of chlorine that we want to measure. Well, we know chlorine, like we said earlier, exists as different isotopes naturally. So we take into account the percentage of each isotope that's occurring. We know there's much more of one isotope than the others. And then we find the approximate average mass of each of the isotopes. And that's what we get the atomic mass from. And that is shown right there in the bottom underneath the element symbol. Now the atomic mass is always going to be a decimal because it represents averages, unlike the atomic number, which is always the atomic number and the mass number, which are always going to be whole numbers. Okay, so this brings us to the very last section, which is the arrangement of electrons in an atom. So here we have another picture of the Bohr model. Bohr was right when he suggested that electrons in an atom have different energies. Those concentric circles signify the different energy levels. So the atoms that are closer to the nucleus are at a lower energy level than the ones farther away. He also said that each kind of atom has a unique arrangement of those electrons. So an atom of this element X has a unique electron structure as opposed to an atom of the element Y, for example. So every kind of atom has a different arrangement for its electrons. Now, we said before that the main difference between the Bohr and quantum model was the location of the electrons within its energy levels. So the Bohr model suggests that electrons exist in a specific location, but what we actually found is that it's impossible to know precisely where an electron is located because they're constantly moving around. So instead of saying, like Bohr, that this electron is located right here, instead we say that these are more like regions. So there's this approximate space that the atom is most likely to be found. And those, instead of I guess, I don't know what he called this, but those regions are known as the orbitals. And again, that region where they will most likely be found depends on the energy level of that specific electron. So this is very important for you to know. This chart right here, there are 7 different energy levels, and each energy level can only occupy a certain amount of electrons. So I actually want you to memorize this chart right here. The first energy level can only occupy 2, second 8, so it kind of I think it doubles as you go farther away from the nucleus and you get into higher energy levels. Okay, so this chart tells you how many electrons each level can hold, but the actual number of electrons on any given level depends on the atomic number of the atom. Remember, Z is referring to the number of protons, which is equal to the number of electrons in the atom. So that number of electrons is going to determine how many of those energy levels get filled up. So they're filled from the inside towards the outside. And here we can see some comparisons. For oxygen, oxygen has an atomic number of 8, meaning that it only has 8 protons and 8 electrons. Now we know from this chart here that the first energy level can only have 2 electrons, the second 8. So we start by filling them out from the inside out. So we have 8 total electrons. We know 2 only fit in the first, the remaining 6 go on the second. Okay, so again, the number of electrons each individual kind of atom has is going to determine how these energy levels are filled up, and it's just in its overall electron structure. So I think this is neon. Neon is different from oxygen. As you can see, it has 10 protons, meaning it has 10 electrons in this case. So here we have the 2 innermost electrons, and the final 8 fill out the second energy level. Now notice, oxygen doesn't completely fill up that second shell because it only has 6 electrons on the outer shell, and it can hold a total of 8. Now that's okay. You will find out later on in chemistry how not having a complete, we call this valence electron shell, affects that atom. You'll also learn about something called the octet rule, but that's not important right now. All you have to know is that the number of electrons that each of these shells can hold, and you just have to know that the number of electrons obviously determines how those shells are filled. Another example here is carbon. I don't know what this is. Calcium. So calcium has an atomic number of 20, meaning it has 20 protons, thus it has 20 electrons. So we know 2 go in the first energy level. The second energy level can only hold up to 8, and you see those are both completely filled. The third energy level can only hold 18. Now notice, it doesn't seem like there are 18 in the third energy level, and that is because we want to put some in the fourth energy level. And now you don't need to know the reason for that. Again, that's something that's going to come up in chemistry. So that brings us to the end. Make sure you have this turned in. If by now you should be able to fill out this chart. This is what we talked about earlier here with the atomic number and finding the neutrons from the atomic number and mass number. If you are still confused, please let me know. And that is what your test is going to cover.